Hey, my name is Sebastian and I want to tell you about my PhD research today. I will teach you how to solve computed tomography reconstruction with neural networks. This is me, clearly enjoying a beer. I'm a fourth year PhD student working with Carola Schönlieb in the Cambridge Image Analysis Group. This is a device most of you hopefully haven't seen yet. It's a computed tomography device designed to look inside patients' bodies. Using this device, we can produce high-quality images of patients' brains, allowing all kinds of medical diagnostics. Let's now have a look at how this machine works internally. This is our patient today, a squirrel. We want to take a computed tomography image of our patient, so we add the device and expose our patient to X radiations along straight lines. The way we can now image the squirrel is by looking at how much radiation is measured on our receiver plate on the right. The signal we measure depends on tissue density. For example, bones absorb more radiation than soft tissue. We do this from any possible direction by rotating our measurement device around the object. This allows us to record this type of measurements, called the sinogram. The challenge of computed tomography is to get back from those to the original image of our patient. Why is this difficult? As a thought experiment, consider for now a checkboard that we're trying to measure with computed tomography. And let's compare this with a plain gray square that we're also trying to measure. As you can imagine, no matter which direction we take our measurements from, we will produce a fairly similar result, no matter if we image the square or the checkboard. This makes it very hard to distinguish those two using computed tomography and makes reconstruction difficult. If we don't use our knowledge that a priori single color images are more likely than images with pixels jumping black and white, we are not able to obtain high quality reconstructions. So in order to obtain good reconstructions, we need to put this additional knowledge into our reconstruction. Here are some examples of the images that we obtain in very low dose computed tomography if we don't put this additional knowledge in. But how can we put this knowledge about our images into the reconstruction? The answer is that using high doses of measurements, we're able to produce a large number of good reconstruction images. Using this collection, we can use machine learning to actually learn from the data directly how good reconstructions are supposed to look like and what separates those from the noisy images we obtain without putting prior knowledge into the reconstruction. Here we see an image of a patient's lung on the top, and on the lower image a bad reconstruction we obtain with very low dose computed tomography. Now we give both of those to our machine learning algorithm, in our case in convolutional neural network. The network is trained to tell apart the true images from the ones we got using a reconstruction without any regularization and stabilization. This gives us a network that can tell apart how true images look like from the images containing the typical artifacts we get in computed tomography reconstruction. We can now use this network to produce better reconstruction images. Let's look at the following new input, again a sinogram taken of a patient. If we just reconstruct the image without making any further modifications to this measurement, we get the typical artifacts that we have already discovered. If now we use our neural network at reconstruction to not only produce an image that matches these measurements, because this would produce something like the image we see on the top, but also to produce an image that our neural network thinks looks a lot like the real images that we've shown it earlier, then we're able to get a reconstruction that looks like the image below. As we can see, it's a much higher and better quality reconstruction. So making the neural network happy and producing images that look like real data can help us stabilize our reconstruction process a lot. This allows us to get from the very noisy images we would get without prior knowledge to images that look a lot more like the lung scans you would expect. I hope you have learned a little bit about how we can use neural networks to make computed tomography reconstruction better. Thank you very much for your attention.